The last speaker of today is Guillermo Matera. I'm really glad to introduce him to all of you. He's from Universidad Nacional de General Sarmiento and from CONICET here in Argentina. And he's going to talk about average case complexity of the Euclidean algorithm with a fixed polynomial over finite fields. And so thank you, Guillermo, very much for being here.
Okay, thank you. And first of all, I'd like to thank Maria, Melina, and Heriberto for this effort to organize these finite field sessions, and of course for inviting me to give this talk. This is a joint work with Nardo, Giménez, Mariana, Pérez, and Melina. And we are concerned with the behavior of the Euclidean algorithms for polynomials over finite fields. So, as usual, FQ will denote the finite field of Q elements, FQ bar the algebraic closure. I will consider the set of monic polynomials of degree D in one variable, say T. And eventually the polynomials of degree at most D, which is denoted by this symbol. And given some degrees, say E greater than D, both of course positive numbers, and a monic polynomial of degree E and a monic polynomial F of degree, monic polynomial G of degree E and a monic polynomial F of degree D, we are interested in analyzing the behavior of the Euclidean algorithm, the classical Euclidean algorithm, to compute the GCD of these two polynomials on average. So, analyzing averages on average case complexity of the Euclidean algorithm is a very classical subject. I mean, there is a number of results. Sometimes pairs of polynomials, as I said before, of fixed degrees, E and D are considered. Sometimes are considered pairs of polynomials of degree E and at most D, typically with uniform distribution. And there are also results going back to Knuth, but for example, in a paper by Kehu, I think, Ma and Joachim von Surgatten, when one considers, say, some operation, for example, a polynomial division or a field division, I mean, a division between two elements in a Q, or perhaps a subtraction or multiplication. It was shown in this paper that, for example, the expected number, I mean, on average, the number of polynomial divisions performed by the Euclidean algorithms is it's very close to D plus 1. And the number of field divisions is very close to E plus D plus 1, and the number of subtractions and multiplications is very close to DE, of course, depending on the cardinality of the field. There are also some results by Norton on average case complexity of some variants of the Euclidean algorithm. There are more refined results by Brigitte Vallée, Valérie Berthet, and collaborators, where they consider several costs associated to the behavior of the Euclidean algorithms. For example, the number of non-zero monomials rising during calculations, or perhaps some costs related to bit length. But anyway, in all these analyses, as I said before, what is the universe of pairs considered is always the set of pairs of polynomials varying, say, two polynomials varying freely between among the polynomials, monic polynomials of certain degrees, fixed degrees. Our starting point for this work was consideration that sometimes there are important, say, tasks, computational tasks that that have, for example, one fixed polynomial. For example, the standard algorithm for finding roots in FQ of a given polynomial starts computing. I mean, the standard algorithm starts computing the GCD between t to the q minus t and f. And therefore, all the previous analysis cannot say anything because you know, we are considering a much smaller subset of the set of polynomials that were considered in all of these previous analysis. So what we wanted to do was to perform the average case analysis of the Euclidean algorithm for computing the GCD of G and F when the highest degree polynomial, say G, is fixed. And that means that from now on, I will be fixing the polynomial G, and then I consider several, say, random variables associated to the behavior of the Euclidean algorithm. First one is the distribution of the degrees of all possible GCDs of G with a given polynomial, monic polynomial of degree D. That means the random variable xg associates to each monic polynomial of degree D the degree of the GCD of G and F. And also going to the average case complexity, again, considering polynomial divisions or field divisions or subtractions or multiplications with elements of the field. We were interested in analyzing the behavior of the random variable, which associates, again, for each f, the number of each kind of these operations performed by the Euclidean algorithm on an input GF. So we were interested in analyzing these expectations and start, say, with somehow in asymptotic terms, in terms of Q. I mean, we are assuming here that Q is much larger than E. We start with the average degree of the GCD, and for the average degree of the GCD, it turns out that this degree depends essentially on the factorization pattern of the polynomial G under consideration. By factorization pattern, I mean a tuple, say for a fixed polynomial of degree E, I mean a tuple lambda 1, lambda E, such that lambda 1 denotes the number of irreducible factors of degree 1 of G, and so on. So our result is the following. Rather than considering the factorization pattern of G, we consider the reduced factorization pattern. That means the number of not the total number of irreducible factors, but the number of distinct irreducible factors of each degree. And if K denotes the minimum of the degrees of the factorization of the irreducible factors of the degree G under consideration, and there is lambda K star irreducible factors of this degree, then the probability that a random polynomial f with say monic with degree D is relatively prime with G is very close to 1, and as close as depending on I mean, on the degree of the minimum irreducible factor. I mean, when as long as this degree is higher, then the probability is much close to 1. The probability of that a random polynomial f is relatively prime with G. And taking into account now the expected degree, well, the expected degree of the GCD is of order close to 0, indeed. And more precisely is of order k lambda k star over q2k. And as I said before, this was important to analyze the average case complexity of the Euclidean algorithm for a fixed polynomial G. We consider 3 different expectations: the average number of polynomial divisions, again taken on all monic polynomials of degree D, and the average number of field divisions between elements of Q, and the average number of subtractions and multiplications. And it turns out that again, what happens in the general case I mentioned before is also reproduced here. I mean, number of expected divisions is also G plus 1, although in spite that the polynomial G now is fixed, and the number of field divisions is of order E plus D plus 1, and the number of subtractions or multiplications is of order DE. With say two side bounds on these deviations, and where one side, the upper side, actually depends on the factorization pattern of G, and we were unable to find a corresponding lower bound depending on the factorization pattern of G, and I will mention something on this issue by the end of the talk. Okay, and I'd like to discuss a bit some of the ideas of the proofs of these results. And we know when we apply the Euclidean algorithms to a given pair, what we obtain is some remainders and some quotients, say H at most D, remainders and quotients satisfying well-known relations required by the Euclidean algorithm. To simplify a bit, say this analysis, we assumed that the classical, say, synthetic polynomial division algorithm is used. The analysis can be modified to take into account more, say, efficient algorithms for polynomial divisions, but for all what I announced, only the synthetic polynomial division algorithms considered. And it turns out that the number of arithmetic operations performed by the Euclidean algorithm is essentially determined by the sequence of degrees of the remainders. And therefore, what one has to do to determine say, an average case analysis is to analyze the distributions of these degree sequences, and particularly the length of these degree sequences. I mean, the number of remainders that may appear for a random f. So critical to our approach was to analyze the number of, say, the set of monic polynomials of degree D for which the GCD with G had degree I for given I, for each I, each possible I. And also another critical set for our considerations were the analysis of what we called the set of monic polynomials of degree D that are generic with respect to G. Generic means that the remainder sequence, the number, I mean, the remainders which appear in the Euclidean algorithms have a maximal possible length, which is indeed D, the highest possible length. We call these generic because we were expecting that this was, say, the Euclidean algorithms for most of the polynomials, we were expecting that had to have a maximal length D. The behavior of the Euclidean algorithms for these pairs of polynomials, I mean, some results can be obtained from for considering separately the behavior of the Euclidean algorithms on each of the BIs and on the set G. And it turns out that, for example, when one considers the set of polynomials f for which the GCD with G has degree D minus k, then the number of operations for each time of operation that we considered is maximized when the remainder sequence has the maximal possible length, which is indeed k. I mean, the degrees of the remainder. I mean, there are k remainders. And on the other hand, for generic polynomials, the sequence of the remainders, there are D remainders. That means that the degree of each remainder decreases in 1, and therefore the degrees of the remainder are fixed, and therefore the number of arithmetic operations for each type of operation we considered is constant. So to establish lower and upper bounds on the expected number of arithmetic operations, well, one can describe this expected number in terms of what happens on each of the sets VI. For one hand, let's say to obtain upper bounds, and to obtain lower bounds, one may just consider the set of generic polynomials. And it turns out that one may rearrange these sums so that these sums can be upper bound in terms of the expected degrees of the GCD, the expected degree of the GCD. And the problem, a big problem, was to prove that that this sum here on the left-hand side is significant. That means that we have a sufficient number of say, generic polynomials with respect to G. And for this, okay, I'm running out of time, and considering that it's Friday and it's the last talk, I'll try to be very brief. We compared, say, the formal execution of the GCD. That means the execution of the Euclidean algorithm on generic polynomials, which are described in terms of its roots instead of their coefficients, which is a key point. And I will be brief here. It turns out that one has a very precise, nice descriptions from people from combinatorics of remainders in a formal execution of a GCD in terms of the elementary symmetric functions in say the set of roots of the first and the second polynomial, and using these descriptions, we were able to taking into account that we had a specialization of this formal execution, because we had to specialize the indeterminate roots of the first polynomial by the roots of the polynomial G. We obtained some characterization of the leading coefficient of the remainders of the Euclidean algorithm applied, say, to G and a generic and a formal polynomial of degree D. And with this analysis of these leading coefficients and a characterization of the property of being generic with respect to G in terms of the behavior with respect to these polynomials, we were able to find a good lower bound on the number of generic polynomials, which asserts that actually we have a high proportion of generic polynomials with respect to a fixed polynomial G. That means polynomials for which the degrees in the Euclidean algorithms decrease by 1. And using these, we were able to obtain a lower bound for our expectation. But and therefore to obtain these two side bounds that we obtain from the deviation from the expected number of operations. To finish, I have to say that some numerical experiments we performed seems to show that actually the number of generic suggests that the number of generic polynomials with respect to G should also depend on the factorization pattern of the polynomial G, but for the moment being we haven't been able to obtain a lower bound on the number of generic polynomials depending on the factorization pattern of G, and this is something an open question that we expect to be studying in the near future. Thank you very much.
Thank you. So are there questions?
I have some questions or comments, right? Very nice, very nice. So, okay. So first, in general, when you see the results on average case analysis, right? As you were saying, you have you normally fix Q. You fix Q, and then you make the degree of the polynomial or polynomials to go to infinite, and you do the derivation like that. Because here you are fixing one of the polynomials to be x to the q minus x or x to the q to the m minus x, whatever like that, then your only choice is to make q go to infinite. Because the other polynomial, after the first division, both will have degree strictly smaller than x to the q minus x or whatever the polynomial was. So that's why I think it makes sense to go to q to infinite. And now, when you go q to infinite in the average case analysis algorithms, you know, that exist, in general, you find a situation that sometimes is called permutation model. So basically, if you do a question for polynomials, and that question you can do it for permutations, right? Like, okay, you're talking about the factorization pattern. Well, the factorization pattern of irreducibles is the factorization pattern of cycles in the permutation. Having no fixed cycle, having this or that, you can translate the equation. And then it turns out that when you make Q go to infinite, what you obtain is sort of the result for permutations. Here is kind of different because you're starting from the Q infinite. But I was wondering here while you were talking whether there is any way of having a situation over the permutation groups where you can sort of see the situation of the GCD. I could not find anything. So do you have some way of connecting this to a similar problem for permutations?
No, actually, no.
Yeah, it sounds weird.
We departed from I'm particularly interested in algorithms for solving polynomial systems. And now we have to make a lot of GCD calculations. And therefore, from polynomial systems, and I at that point I considered Q, the Q that I'm interested in is large. I mean, then I arrived at this situation, and a priori I don't see any way of connecting GCDs with cycle problems. But
yeah.
I don't know.
Yeah. I think I thought about this many years ago and I arrived to nowhere. So yes. So anyway, so very interesting. The other thing is, so in a way, what you're obtaining are bounds and estimating the expectations, and probably you can also get deviations. Now, this is sort of the situation of the Keju-Ma and von Surgatten paper. They also do this analysis, and very exact. They don't do just bound, they do exact. And so it's very technical, let's say. But they cannot really produce limiting distributions or anything like that. While Brigitte Vallée and collaborators can produce Gaussian distribution for the number of steps of the GCD and things like that. So a lot of more probabilistic picture, a statistical picture of what is going on. So do you think that there is any hope that you can get these type of things here, or you will sort of know up to variance and we are happy?
I'm always interested in Brigitte's approach. I mean, for example, connecting the Euclidean algorithms with continued fractions, for example. And there is a very, very interesting formulas for continued fractions, also by these people of combinatorics I've mentioned before. And that may give me, say, some hope that perhaps I can connect. It's always something I very, very much like to be able to do something to use these say tools using continued fraction expansions and things like that. But
right.
For the moment,
yes. She has this, the operator, right? She moves into analysis, and then she managed to get it through Reuel operators and asymptotic techniques, right? Yeah, I don't know whether there is any chance here, but I think it's very useful because really most of the uses of the GCD are for polynomial of this shape, right? You have one of the polynomial, normally it's x to the q to the n minus x, because you want to have the divisors of n, right? All the reducible factor with degree dividing n. So you normally take the GCD against that polynomial, right? But so it's very useful. You talk about the average case analysis of a GCD, but then taking uniformly random. Well, those are not the ones that are used in most of the algorithms. So, so I think this is very useful, to have this thing. Maybe can one more thing, or probably I already hopped too much, or one more. So do you have an intuition why, when you fix the one of the polynomials, you are still getting the leading term to be the same for the average number of the division, etc., You lost in the error term, but you do not lose in the main term. So my question is, do you have an intuition? So yeah, sure, this is obvious because when you divide this and that, obviously you will have the same number of divisions or whatever. Do you have an intuition like that?
I'm not sure if I understand properly the intuition on what.
Okay, go back to the formulas that you have, and I'll show you exactly where. Oops, right here. So when you take a look at the theorem, if maybe I understood wrong, but those are not, the terms are deep, you see for division is d+1, right? Etc. So these are exactly the same values that you have before.
Yeah.
Right. So my question is, any intuition why this is happening?
For example, for the number of polynomial divisions, it has to be, it's connected with the fact that most polynomials are generic with respect to G.
And then because the set is essentially the same. Okay. Okay, I would need to see the paper, but okay. Okay, good. Thank you.
Well,
sorry.
No, yeah, thank you, Daniel and Guillermo, for this interesting talk. And maybe you could continue talking in the forum so we can all learn more. And if there are no questions from anyone else, I think that we should thank Guillermo. And I also want to thank all the speakers of this session for this day, and of course, all the participants for being here. And we'll see on Tuesday next week. And well, thank you very much.